Welcome everyone to the afternoon keynote. What I want to talk about this afternoon is something that we have struggled with in software, and it's this idea of being able to support constant change, because change keeps happening to us from several different vectors, and we constantly have to incorporate that, and it's something that we have traditionally struggled with, and only recently have we figured out ways to make this better, and that's exactly what I want to talk about this afternoon. So let's first talk about the nature of change, because most of you think of change as just one kind of thing. But for us in the software world, it's actually two kinds of things. There's business-driven change, and there's technology-driven change. Business-driven change are things like changing requirements. So we have a requirement to do a particular thing, and then our business changes our mind, or our market evolves, and we have to change that and do something else. Or maybe we merge with another business, and they have a different way of doing things, and that's all things that are driven by the business, and that's part of our job as technologists, is to manage that kind of change as it comes along from the business. And in fact, that's really been the focus for the last 20 years or so of most of the books on agile software development have been focused exactly on this. How do we manage this kind of business-driven change that's happening in our ecosystem? But the other kind of change we have to think about is technology-driven change. It's the change that gets imposed upon us by both decisions that our business make and also by the ecosystem that we live in. So let's talk for a moment about technology-driven change and this idea of the dynamic equilibrium of the software development ecosystem. So if you think about the software development ecosystem, it consists of all the tools and frameworks and best practices and approaches that we have for building software up until about 5 minutes ago. That is the software development ecosystem, and that is the place that we all work and live on a regular basis. And it's an equilibrium, meaning that you can understand it and make plans against it, etc., but it's also an extremely dynamic equilibrium, meaning that it can change fundamentally without letting you know that it's about to change fundamentally. And a great example of how dynamic this equilibrium is a few years ago when Docker hit our ecosystem. Once Docker hit our ecosystem, it fundamentally changed it forever. Now, even if you're not using Docker yet, because it now exists in our ecosystem, you have to think about that as you start trying to make plans for things in the future. And so constantly things are happening in our ecosystem that impacts our ability to make decisions about things, and this is the reality of the world that we live in. But this is really problematic for some roles like enterprise architects who are tasked with long-term strategic planning. How in the world can you plan strategically in an ecosystem like this? I'll ask you guys a question. I've been talking to enterprise architects literally all over the world for the past couple of years, and I keep asking them this awkward question, and none of them can give me a good answer. So maybe somebody in the audience here can give me a good answer to this question. Can you tell me with certainty exactly what JavaScript web framework you'll be using 2 years from now? Anybody? You can't, because it probably hasn't been written yet. How can you possibly do long-term planning in a world like that? And of course, the answer is you can't. You have to be able to adapt and be able to support constant change, because that's the reality of the world that we live in. So let's talk about how we manage this kind of change, in particular this kind of technology-driven change, because as I said, we've gotten pretty good at managing the business-driven change. This is the one that we've really struggled with. And this also has two interesting aspects. One of these are technology-driven change that are forced by the business, because the business decides they want to start doing mobile development or want to change platforms or fundamentally change the performance or scalability or something like that within their system. And this is really what we've been sort of attacking in the Agile world for the last while. And in fact, the first real steps toward making that a possibility were some observations that were made in the early 90s. So it was a very common practice in the early 90s that developers would work essentially in isolation from one another, and at the very end of the project, they would take all the stuff that they'd been working on and consolidate it all together in this big giant integration phase on projects. This was a standard phase on projects back in the 70s and 80s and early 90s, And not surprisingly, this is a pretty horrible process. In fact, there's a pretty strong correlation to the size of the project and how awful this integration phase was. A bunch of really clever developers in the early 90s had worked collectively on hundreds of software projects, and they were depressed at how subjective and arbitrary most of the software processes were. And they said, okay, and they didn't say it exactly like this, but what they wanted to take is more of an engineering mindset for software development. So they really stepped back from all the standard processes at the time and started saying, well, let's take the things that we know have worked well in the past and push them as hard as we can and see if we can make a better way to build software. And they're the ones who invented this idea of continuous integration, because they made the observation, you know, in projects where we were really eager to integrate stuff, we didn't have to deal with this big integration problem at the end, and they invented this idea of continuous integration where we should integrate really early and often, and ended up with a mantra, everyone integrates at least once a day. This is, of course, what we now know as continuous integration. Now, traditional developers who heard about this, that you integrate every day, now to them, integration is the worst part of the project. And when they hear that you're integrating every single day, they think that means every day is the worst day ever. But it turns out that an interesting side effect came up from continuous integration, that if you do it every day in small steps, it never grows into this dragon you have to slay at the end of the project, because you've managed it in little bitty tiny steps, and you've managed that change in a way that didn't grow into this big huge problem toward the end. These were, of course, the extreme programming guys. They founded this methodology called extreme programming that was purely based on empirical evidence. We want to know things work, and then we'll just do that to the extreme. That's the idea of extreme programming. This is a little too ESPN2 for some people, because the name sounds kind of crazy, and it sounds like you're required to have tattoos and piercings before you can do extreme programming, but that's not true at all. It's actually an extremely disciplined way of writing software, and it's one of the few methodologies that actually includes engineering practices, including things like pair programming, continuous integration, because they had a real engineering mindset toward building software. But even with the XP guys, there were still some gaps in the things that we could do to really fully support constant change. They filled in a lot of the details around iteration and how feedback loops work, et cetera. But that was in the early 90s. We didn't stop innovating at that time. We kept going and ended up building a whole bunch of modern engineering practices in the book Continuous Delivery by Jez Humble and Dave Farley. Now, continuous delivery is really just a bit of genius marketing, because if I were publishing this book, I would have named it something entirely accurate but very boring, like efficient engineering practices for software projects or something like that, and we would have sold 12 copies to my family, and that would have been it. But by giving it a name like continuous delivery, it's a nice, catchy name. And really what this is, if you look at it, it's the updated engineering practices from the XP guys, but updated into the 21st century, because now we have more capabilities to do things, because now we have things like machine provisioning, and we have all these new possibilities around DevOps. So Michael Nygaard released DevOps, and the DevOps idea came to pass. We now have the techniques around infrastructure as code, and I'll talk more about that in a second as a way to remove variability. Things like refactoring databases. I want to mention this book because toward the end of this talk, I'm going to mention my latest book, which is Building Evolutionary Architectures. This book came out 10 years ago by my colleague Pramod Sadlage and Scott Ambler, called Refactoring Databases. And notice what the subtitle of this book is: Evolutionary Database Design. This is the perfect companion to evolutionary architectures, is evolutionary database design, because it turns out if you need to build systems that change, you need to be able to change the relational database as well. And so this is literally just a book that's about 10 years ahead of its time, but fortunately it's still available, and it's still a classic in the software engineering world. But let's talk about some of the lessons that we learned from these books and since then about how do we really fully support this idea of constant change. One of the things that we've realized is that you have to expend energy on software projects to make things happen. And a lot of times we end up expending energy in places that are not useful. We'd really like to expend most of our energy in going to one direction, but we end up expending energy in going to a whole bunch of different directions, meaning we can't expend as much energy going in the direction we'd like to. So part of what we'd like to do here to support change is build some constraints around the things that we spend energy on so that we don't spend energy on things that we don't need to spend any more energy on. And of course, this begs a very interesting philosophical question. What is exactly the correct level of constraint to achieve this? But we've already seen some examples of this. So for example, there's virtually no organization that benefits from having every one of their servers being a handcrafted artisanal snowflake server. There's just hardly any possible advantage to that. We've learned that that is not a good kind of variability because it allows all sorts of interesting things to happen that are not interesting in a good way, they're interesting in a bad way. And so if you lock those things down, then you stop worrying about bad things happening. In my Stories Every Developer Should Know talk, I talk about this tragic case of Knight Capital, which ended up being bankrupt essentially because they didn't have good DevOps practices. They deployed new code to 7 of their 8 servers, and then chaos happened, and that's exactly the kind of variability that has no benefit in your organization. And so that's actually one of the secrets to supporting constant change is to remove variability in a variety of different places. So let's talk about ways to remove variability. So this is exactly the case where you don't want lots of different things working independently of one another. Instead, what you want is unified versions of things that work in exactly the same way so that you don't have to worry about them doing something that you don't want them to do. So let's talk about techniques you can use to remove variability in projects, and I'll talk about 3 of them. Automation, some aspects about reuse, and finally, mutability. The first of these is automation, and this is a lesson that came from both extreme programming and continuous delivery. This, of course, the new artifact that continuous delivery gave us is this idea of a deployment pipeline. But this is really just a way to automate more and more of the things that you have to do on every single project. And so deployment pipelines are sort of continuous integration on steroids with stages, and these typically include things like machine provisioning and other sorts of advanced things, including maybe integration testing and some other advanced engineering practices. But it turns out that one of the really nice things, so a lot of people view this as just a first-order benefit, and it is a first-order benefit, but there are several second-order benefits you get from this as well, sort of side effect benefits that you get by having this in place, and I'll talk about several of those. One of them is this level of automation enables the kind of immutability that you want to lock down things that you don't actually want to change. And the common application that we've seen of this over the last few years is this idea of infrastructure as code. Stop handcrafting machines and touching binaries, but instead capture them in source code. And this has a bunch of advantages. You have the definition, which documents the machine as well as defines it. This lets you have self-documented system and processes that are executable, so you know that the documentation is not lying about what it does. This allows you to version all the things, and because you're building it up incrementally, it encourages you to build small incremental changes to your infrastructure rather than big, unreproducible changes all over the place. Allows you to continuously test systems and processes because you can automatically provision machines. You can put these in deployment pipelines and run automated tests on them because you know exactly what you're building every single time you go through this. This allows you to do small changes over large batches and manage those things in a much more agile and deterministic way. And this allows you to keep services available continuously. And of course, this book that came out a couple of years ago now, Infrastructure as Code, is a great highlight of the advantage, the benefits of doing and treating your infrastructure immutably. And part of what we're doing here is trying to destroy these handcrafted works of art and getting rid of snowflake servers and instead creating these immutable servers. And in fact, a common practice now is this idea that once you created a server, you never actually change the binary. If you need to change it, you change the source code and then regenerate the binary. That way you control the change because you have a single source of truth about that. And one of the huge lessons that we learned by automation in the operations space is that when you have a bunch of workers, like operations folks, doing manual ad hoc stuff over and over again, things always fall through the cracks. And by automating those things and by reducing the number of definitions you have, then those things don't fall through the cracks because you don't have to constantly be vigilant about them because your automation is handling that for you. Another thing we should think about from an immutability standpoint, and this is a lower level development kind of thing, is immutable dependencies. So one of the interesting problems that is pervasive across all of our technology stacks right now are transitive dependency management. And pretty much every platform suffers from this, but maybe none more so than the JavaScript ecosystem. This is a dependency graph from a JavaScript project that has lots and 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 lots of transitive dependencies based on it. And the interesting thing about this problem for us is that it is uniquely ubiquitous. Every single programming platform suffers from this dependency management problem because we're constantly trying to figure out ways to reuse code, and so this is part of how we wire in dependencies, but it always becomes so complicated we always have to end up building tools to do this. So we have Maven, and we have Bundler, and we have Pip, and Fabric, and all those things, and there are, 16 different ones in JavaScript right now, and of course some of the ones in JavaScript require you to install the previous transitive dependency management tool so that you can get the dependencies for the new transitive dependency management tool. So we're building castles on top of sand, on top of sand, on top of sand, and this is one of those problems that I think we're eventually going to have to get a handle on. One of my colleagues, who's based in the UK, who's also named Ford, but he's not related to me, makes a really interesting observation that dependency management will be our go-to considered harmful moment in software. This is very famous that Edgar Dijkstra, back in the late 60s, did a famous talk where he said that, you know, maybe using unrestricted go-tos is not the best way to write software, and it almost caused a riot because nobody could imagine writing code without that. The first step in solving a problem is identifying the problem. I don't have a solution for this, but I've identified it for you. So now it's your job to go fix this problem. So I've done my work. I've identified this as a big problem, so go fix this now. But there are some tools starting to come into this place. And one of them I'll point you to that will be on the next technology radar actually is Dependabot. This is a tool that allows you to manage your transitive dependency management, because one best practice here is, so it's a little bit crazy to wire your project to some unknown resource out on the internet that some dude in the basement owns somewhere, because someday he's going to get mad and want to take all of his toys home and then remove his stuff, and you're wired directly to his basement, and it's going to cause havoc on your project. This is exactly what happened with leftpad.io. The dude who wrote it got mad about something that happened, and so he took all of his code away, and Node and Angular and a whole bunch of projects would not build anymore. I think it is professionally irresponsible to wire your fate to some random thing out on the internet. And so that's exactly what Dependabot does. It creates a level of indirection. You pull dependencies from the internet into Dependabot, and then from Dependabot into your project. So that when leftpad.io disappears, you reject that pull request from Dependabot. And don't break all of your software for 2 days because you've wired yourself to some random thing on the internet somewhere. This is really about dependency governance and managing our reuse and this transitive dependency management, which we're going to need to do because this is a really interesting proof of concept that came out last year or so. This NPM only lasted about 3 hours for obvious reasons when you see it, because you know, NPMs, when they install, they can run a shell script to complete that installation. And this particular NPM, as a proof of concept, the shell script it ran to complete its installation did an rm-fr/. So what this NPM did was remove all the stuff on your hard drive to make room for more NPMs that you could download and install, except that you no longer have an operating system or anything on your hard drive anymore. Mark my words, NPM is going to be an attack vector for developer machines pretty soon. It's already happened to the Chrome developer toolbar. Became an attack vector for viruses and other malicious things. This is a wide open attack vector for a lot of developer machines that you should be careful about this. You need something between you and the random crap on the internet because some of that stuff is dangerous. And so you need a layer in between you. That's really this idea of dependency governance. So the last one of these I'll talk about variability is reuse and code reuse and the many, many, many ways we try to use, reuse, and abuse code over time. There's a great quote here by John D. Cook, who's a mathematician and also has some great quotes about things. And this is a great quote. Software reuse is more like an organ transplant than snapping together Lego blocks. We've been sold this idea that, well, as long as you build components, you can just snap them together like Lego blocks. But the practicality of that is not true. It's a way more like an organ transplant than it is putting together Lego blocks. But we learn every time, it seems like every time we try some technique, we learn from that and take 2 steps forward and 1 step back, maybe, if I'm being charitable. So let's look at exactly how this played out in the architecture space over the last decade and a half or so. And 2 different fundamental ways to reuse stuff in architecture. So back in the enterprise service bus driven service-oriented architecture day, one of the goals of architects in this world was to try to consolidate stuff as much as possible. We want to try to, if we notice that we use customer over here and customer over here, that means, oh, we should try to unify those things, because it was exactly this scenario. So let's say you're running an insurance company, and you have home and auto, and you have commercial, and you have casualty and travel, et cetera. And each one of these guys has some concept of customer in it. What architects were taught in this day was you're supposed to look for this and go, oh, well, hey, look. They all say customer, therefore they must be the same kind of thing. And so what we should do is consolidate all that code together and create a customer service that knows everything we know as an organization about customer, and then we'll just couple all these things to that guy when we need customer. This seems like a reasonable thing to do. The problem is, the side effect of this, it doesn't work well for exactly the kind of change I was talking about earlier, which is that business-driven kind of change. Because some of you have lived through this exercise where you've said, as the architects, all right, I'm sick of these shifting definitions. We're going to take all the business people and lock them in a windowless conference room and not give them food or water until they tell us what a customer is here. Once and for all, we got to know. And even if you've gone through this exercise, they do this exercise called JAD exercise, joint application design exercises, where you're supposed to drag everybody away from their desk and get them all to agree on what we mean by customer. Even if you could make that happen, tomorrow we're going to merge with another company and all bets are off. Because it's going to fundamentally change constantly. Remember, everything constantly changes. And this idea fundamentally presupposes that we're going to get a single representation and then we'll be able to drop the whiteboard marker and walk away and never have to touch it again. But it never happens because everything changes all the time. But see, there was some benefit to doing that in DSB world, because we did get some benefit from that in this area around these kind of infrastructure services like logging and monitoring and that sort of stuff down here. It is actually beneficial to get everything in the organization around a single version of a monitoring tool, single version of a logging tool, single place to upgrade all those things. That's really nice. So we got reuse benefit from that, but we tried to apply that philosophy to every single thing in our project, and it turns out the domain side of this was a giant headache because it was really hard to adapt to the changing world that we were in because all of our working pieces were spread out everywhere. Fast forward to the modern architecture, which is microservices, which is a shared nothing kind of architecture. The pendulum has swung completely in the opposite direction. And in this world, if you have a service like catalog checkout, and it may have the concept of a customer, and you have another service that does shipping, and it may have the concept of a customer, those are never meant to be unified as a single shared thing. Each bounded context has their own idea of a customer, and if you need to share information between those guys, you share them via messaging and just send the details of this customer to the details of that customer, and never try to unify in a single shared class, because it just doesn't work well. Because we realized in the microservices world that coupling is really deadly dangerous. That coupling is the thing that makes it hard to make changes to one versus the other. And if you decouple them, you free up the ability for each of those to change more independently. We thought about this a lot in the Evolutionary Architectures book, and we came up with an observation that was sort of surprising even to us, excuse me, that the more reusable something is, the less usable it is. if you build something, well, thank you. I got a round of applause for that, so thank you very much. So if you build something to be as ultimately reusable as possible, and now need to reuse it for one thing, it's really hard because you have to instantiate a whole bunch of stuff into it that doesn't really need to be there. And so there's this ironic thing that the more you try to reuse something, the less usable it becomes. This advice also exists in the use before reuse advice that has existed for a long time. That's exactly where that comes from, because we get caught up in this idea of reuse and we end up chasing that before we chase the idea of actually reusing stuff. But now, though, it seems like we've given up all the advantages that we had in ESB, because now we don't have any coupling at all, and so now we got a big headache with things like logging and monitoring and all those things that we would like to have consistency for, except that we have solved that problem in a slightly different way. So if you look at microservice diagrams, very often they include this idea of a service template that each one of these microservices sits on. And that service template is the thing that unifies all these operational concerns. Things like logging and monitoring. These are tools like Dropboot Wizard or Spring Boot. The idea is that you instantiate the service template, build your domain behavior inside there, and then a shared service team manages the logging tools and the monitoring tools, and that allows them to upgrade all those at one time just by upgrading all the service templates. So this became a popular pattern in the microservices world, and that in turn led to the rise of this idea of service meshes. So here's the idea of a service mesh. This is that realization that every one of the services you end up creating here ends up with the same kind of operational stuff in it. They all have service discovery, they have circuit breakers, maybe they have elasticity built in at the service template level. And at some point you realize, you know, those really, we should unify all those things together. And that's when they created this concept of a sidecar. So a sidecar is basically the service template, and that includes all the operational aspects of your microservice. And the idea is that now all those sidecars can be consistent and managed through the service template, and now all the domain behavior can be separate from those things. And now the next step of that is wire all the sidecars together. And that's what a service mesh is. It's the ability to wire the sidecars together so you could tweak monitoring at a global level just by changing the values of the sidecars, and in fact create things like dashboards on top of your sidecars. Now you have a way of managing that operational concern that is now reusable and consistent across the entire architecture, but now we're not forcing the same level of reuse on our domain classes, which are still free to be as different and as duplicated as we need them to be within this world. This is a great example of how thinking about things as fundamental as code reuse evolve over time. We still have the same things that we need to reuse. We want to reuse operational concerns like logging and monitoring. We just figured out more clever ways to do that. This is a great example of that kind of constraint that I was talking about, building the kind of constraint around the things you want so that you can push forward in a faster direction than you could by letting them run wild. And so while we end up abusing reuse a lot, we still need to be able to reuse code, but we need to be able to reuse code carefully. We always think of code reuse as purely a virtuous thing with no downsides, but often there are some downsides and trade-offs, and you have to think about those things. And as I illustrated, we evolve the way we think about reusing the things that we benefit from duplication and getting rid of the things that we don't benefit from that duplication. So let's talk about a few more ways to support constant change. And one of those ways is to rethink the traditional ways we've been thinking about enterprise architecture. As I said, I've been talking to a lot of enterprise architects and a lot of our clients around the world over the last couple of years, and I can't think of any other role in software that has changed more fundamentally over the last few years as the role of enterprise architect. Because if you look at their standard playbook from the late 20th century, a lot of those things have fundamentally changed in our ecosystem, and a lot of enterprise architects have not adapted well those changes, including constraint, but they don't usually use the word constraint as an enterprise architect. Instead, use the word governance. But I maintain that we've just misinterpreted the word governance, because the word govern has multiple meanings, and I think we've been using the wrong definition. So here's one definition. To govern is to control, direct, or strongly influence the actions or conduct of, to exert a determining or guiding influence in or over, or to hold in check. This is what enterprise architects think their job is. And here's just an interesting aside. You notice the root of this word, I love words, words are cool. The root of this word is actually from the Greek kubermon, which is of course the root of Kubernetes. So there's some little synergy between Greek words that show up in the software world. But my suspicion is that this is what enterprise architects have thought their job is to control, direct, and control the actions and conduct of. And you see this very often in this idea of monolithic governance. To achieve cost savings, we want to unify on the same technology stack for all applications. But let's actually walk through that exercise. As an enterprise architect, to minimize costs across the organization, I want to unify on singular technology stacks to solve all these problems. And so now I'm tasked with choosing a relational database. How am I going to choose a relational database? Well, I need to go to every team that uses a relational database and find the team that has the nastiest, gnarliest relational data problem, and I have to choose a relational database that will solve their awful problem. Then I have to go to the enterprise architects, or the integration architects, and find out what's your nastiest, gnarliest, awfulest integration architecture problem, and I have to pick some sort of mechanism that'll solve that problem. Then I have to go to the reporting team and find out what their awfulest, nastiest reporting problem is. And I've got to choose a technology stack that'll solve their problem, and I'm going to unify on this technology stack I've come up with, which means that every single project in my organization is over-engineered. Because the data guys don't need the heavy-duty reporting stack, but I'm forcing it on them because we're unified on this stack. Most people who need a relational database don't need the industrial strength relational database, but if we unify on one, then you have to deal with the complexity of the most complex problem of everybody. And so the side effect of this monolithic governance model is you force over-engineering to everything. Everything is massively over-engineered in your entire organization, which is not the thing you wanted. Remember, the goal was to reduce cost. Let's unify. But now what I've done is driven costs sky high because now everything is massively over-engineered. Now it's hard to debug stuff, etc. This is exactly where the thinking came from in the microservices world of this decentralized governance model. Let individual projects pick the technology stack that's most suitable for the problem they're trying to solve. This is not an attempt to let 1,000 flowers bloom and let every project have their own artisanal development stack that nobody else can understand. It's really this goal of stop over-engineering everything to death, pick just the technology you need to solve this problem. Some things need giant scalable solutions and some things don't. And if you have that singular model in mind, you end up chasing that path whether you want to or not. I think what govern should have been for governance is this alternate meaning to serve as a precedent or deciding principle for. Modern enterprise architects who are successful are not trying to cram a heavyweight cost savings governance model down people's throat. They're trying to figure out ways to guide projects to make them fall into success. What can I do to remove friction from your project to make it successful? I still have to think about unifying things, concerns across the enterprise, like operational concerns, like logging support, etc. But what I want to do is build facilities to make it easy for teams to adopt those things, not force them down their throats, because if you do that, then you'll get a lot more adoption, and you get way less over-engineering. The 20th century governance model was very much a cost-saving trumps any sort of guidance, and in fact, the cost-saving is the guidance. We've seen a definite shift in that idea in the 21st century that is way more about guidance now and much less about cost savings because, of course, this happens a lot in software. The thing that you did to try to achieve cost saving did exactly the opposite. It drove costs way up by over-engineering, and so this actually ends up being a better model in a lot of cases. But we're also pragmatists. You probably don't want 50 different technology stacks in your organization. And so one of the things that we identified in the evolutionary architecture book was something that we're seeing a lot of our clients doing, which is what we call the Goldilocks governance model. Pick a small technology stack, a medium technology stack, and an industrial strength one, and when problems come along, choose the right technology stack for that shape of problem. This still gives you some benefits of fungibility across projects because you can now leverage some of the same training, but now you're doing a lot less kind of egregious over-engineering. And whether you have 3 of these or 4 of these, that could be determined within an organization. This gives you a lot more flexibility of building the right thing right without trying to force the same technology on everybody. This is a great example of how the thinking around governance has evolved over the last few years. So these are all things that are required by the business, technology-driven changes that are required by the business. Let's talk more directly about the changes that are purely forced by our ecosystem. And this leads me to talk about the subject of my most recent book and the subject of a lot of research and development over the last year, a couple of years or so, this idea of building evolutionary architectures or architectures that actually support constant change. This has been a traditional problem in software architecture. In fact, the colloquial tongue-in-cheek definition for software architecture for a long time was the stuff that's hard to change later. That's how you identify architecture versus design, the stuff that's hard to change later. But we need to be able to change stuff in software. And this gets exactly back the dynamic equilibrium problem that I talked about before. So when you're going to build a piece of software, you've decided that I want to use software to solve whatever this problem I have is, you have requirements. But that's not the only thing you have to think about when you build software. You have to think about all these other characteristics in your architecture as well. Things like scalability and performance and auditability. And in fact, the real craft and skill of architect is given requirements, given these external things I need to be able to support, how can I best trade off all these concerns? Because you can almost never maximize all of them. That's why you hear the word trade-off so often associated with software architecture. So for example, if you want to increase security, you're almost certainly going to decrease performance because now you're doing more on-the-fly encryption and secrets hiding within directions, et cetera. And so that's really the job of architecture, is balance all these opposing forces and come up with a design. The problem is, there are a lot of these things you can support. Here's a partial list from Wikipedia of things that you can support from an architectural standpoint. These are colloquially known as the illities of software architecture because so many of these end with the word illity. What we're trying to do is add another item to this list, this idea of evolvability. But what does that mean to have an evolvable architecture? Well, let's say that you've chosen performance as one of your primary important characteristics of this architecture. Having an evolvable architecture means that as change occurs in the system, my performance doesn't change. In other words, the things that I've chosen that are important, I maintain the importance of those things as change occurs over time. And so in many ways, evolvability is a meta characteristic because it wraps the other characteristics and protects them from degradation and change over time as change occurs in my system. And as we've noticed, everything changes all the time. And this is a big problem for roles like enterprise architects because how's long-term planning possible when everything's constantly changing in unexpected ways? How can you possibly do 5-year technology plans as an enterprise architect? But then you have to ask the question, well, why were you trying to do a 5-year plan? It's like, well, we try to do these long-term strategic plans because change is expensive and difficult, and we want to try to minimize that as much as possible. But what if change wasn't as expensive or difficult? What if you could more easily adapt to change rather than predict it? Because our crystal balls are terrible, and they're not going to get any better, but we can get better at adapting to that constant change as it comes along. But one of the things that we discovered as we were writing this book are a bunch of secondary effects of having an evolutionary architecture, and here's one of them. Let's say that as an architect, you come up with a beautiful, elegant design that balances all these opposing concerns and requirements, et cetera, and you create that design and hand it over to developers to implement. And they mess it up. They start compromising and cheating and breaking things. So the other question you have as an architect is, once you've designed an architecture, how can you prevent it from gradually degrading over time? If you've chosen performance as a really important thing, how do you know that you've maintained performance over a long period of time? These are both things that are touched on by this idea of evolutionary architecture. So let me give you our definition. Anytime you try to create a new industry term, you have to create a concise definition. So here's ours, and I'll describe this definition to you in 3 parts. Excuse me. An evolutionary architecture supports guided incremental change across multiple dimensions. Let's talk about the guided part first. So one of my co-authors for this book, Rebecca Parsons, who's the CTO of ThoughtWorks, is a PhD in computer science, and she's done some work in the evolutionary computing space. And the evolutionary in our evolutionary architecture is more closely related to evolutionary computing necessarily than evolutionary biology. And we borrow a concept from evolutionary computing. So when you're creating a genetic algorithms have well-known techniques where they mutate themselves every time they go through a generation and then try to produce a new result. When you're trying to design a genetic algorithm, what you want to do is you're trying to achieve some specific outcome. And the genetic algorithm is going to generate potential solutions for you. You need to evaluate every solution it creates to say, is this better or worse than the last one, because you're trying to get to some end goal. That's what a fitness function is in evolutionary computing. It's an objective function that lets you evaluate how close you are to your goal. So let's say you were designing a genetic algorithm for an airplane wing. Every time it produced a new design for an airplane wing, you would evaluate it in terms of lift and aerodynamic capabilities and materials and manufacturing costs. That would be the fitness function for an airplane wing. We've borrowed this concept and created the idea of an architectural fitness function. This is a fitness function that gives you some objective integrity assessment for one or more architectural characteristics. It's important to point out here that this is really just new nomenclature, just a new name for something that existed for a long time. Because look at our definitions. Anything that gives you an objective assessment for some important part of your architecture. And so some metrics, tools, and tests that have been around for a long time qualify for this. So let me give you some examples of this to give you more of a concrete representation of this. So we created a bunch of categories of fitness functions, and I'll show you a few combinations of these now. An atomic fitness function is one that only looks at one characteristic of architecture, whereas a listic one looks at a combination of features in architecture. A triggered fitness function is one that's triggered by some event, like a developer running a test, or a continuous integration triggering some sort of build, whereas a continuous fitness function just runs all the time in like a production ecosystem or something like that. So let me give you a few examples of these guys. So here are some examples of a triggered atomic fitness function. So let's say you're an architect on a project and you'd like to be able to control the directionality of imports on your project. So you have packages for persistence, web, and util, and it's okay for persistence to import util, and it's okay for web to import util, but you never want util to import web, because now you're creating cyclic dependencies between your packages, and you're messing up the semantics of your package structure. You can wire in this rule and use this very old metrics tool in the Java world called JDepend, and now if a developer cheats and does this, it actually fails this test, and that code doesn't make it into your code base. This is third architecture. We have a presentation layer, a service layer, and a data access layer. And you design those layers for good reasons. And as soon as you give this to the messy real world to implement, the reporting team is going to come to you and say, hey, it takes too long to get through all those layers. I need to go directly from the presentation layer directly to the data access layer and bypass the services layer. As the architect, you don't want them to do that because you built those there on purpose, but how can you prevent that from happening? You could do a manual code review. So on a regular basis, the architect could go and review everybody's code to make sure that they're not cheating on this. But remember the lessons we learned from operations? Manual things, ad hoc, done over and over again. What's the side effect of that? Things always fall through the cracks. That's where governance is right now in architecture. Manual processes, ad hoc, over and over again, things are falling through the cracks. There's a tool called ArcUnit that allows you to build fitness functions, including one that manages layered architectures like this. And it has a really nice Hamcrest style matcher. So look at the definition of this rule, which is really nice. No classes that reside in a package service should access classes that reside in a package controller. Now as the architect, I can put this test in place, and I can stop worrying about developers cheating on the architectural design I have created, because now I have a fitness function that guarantees the design of my architecture, and I have a check in place every time somebody checks into the code base to make sure that they haven't violated that rule that I've set up. You can set up lots of rules like this using tests and other mechanisms to make sure that you preserve the important parts of your architecture. But let's look at an even more interesting example, an example of a holistic continuous fitness function. Now, holistic means that it concerns more than one architectural characteristic, and continuous means it just runs all the time within your architecture. One of the best examples we have of one of these that already exists out in the world is Netflix's Chaos Monkey. I'm sure you're familiar with Chaos Monkey and how Chaos Monkey came about. Netflix, when they decided to host all their stuff on Amazon, realized they didn't own their operations anymore, and so they created the original Chaos Monkey. And what it would do is go to an AWS instance and make it start misbehaving so they could see how their architecture would react to that. That was immensely successful, so they ended up creating and open sourcing an entire simian army of all these monkeys that do various things. So I live on the east coast of the US, and I have one of those Ring doorbells that when people walk up to your door, you get a little video. About a year ago now, Amazon East went down. You probably read about that. Lack of automation, by the way, allowing somebody to type in 100 where only 10 should be allowed, but that's beside the point. But automation's a good thing. So Amazon East went down. It turns out that when Amazon East is down, all the magic drains right out of my doorbell, and it's just a regular doorbell now. No videos if Amazon East is down. But when Amazon East was down, Netflix stayed up. And it stayed up because of the Chaos Gorilla, which simulates an entire data center going down, and when it happened, they survived it. But here's an even better example of this idea of a fitness function. One of the monkeys is called the Doctor Monkey. And all the Doctor Monkey does is go around to each service that's running in production and make sure that all their RESTful endpoints are configured correctly. And if they're not, it kicks that out of production. Now, for all of you developers and architects in this room, how many of you are using RESTful endpoints somewhere in one of your applications? You don't have to be shy. There's a lot of hands here. Now, of the people who raised your hands, how many of you will guarantee me that every single one of your RESTful endpoints is configured correctly right now? You can't do that, can you? I bet you'd like to be able to do that, wouldn't you? Because if you worked at Netflix, you would never worry about that, because they have a real-time, continuous check running in their architecture that makes sure that RESTful endpoints are never misconfigured. So they never do code reviews, they never lose sleep, and they never deploy services with misconfigured RESTful endpoints, because they have a real-time fitness function running, managing that governance process for them within their architecture. This is a whole category called chaos engineering, which is all these holistic continuous fitness functions that are testing your architecture. They've just released a book from Netflix about chaos engineering, and they make an interesting point. It's not a question of if your project's going to die at some point. It's when. And how are you going to react to that when it happens? It is naive to think that you can prevent it from ever breaking. You're better at embracing how it's going to break and managing that instead. So those are fitness functions. Let's talk about the incremental part of our definition. And this really belongs in two parts: the operational side of how you deploy things in this kind of world, and I'll give you a case study about that in the end here in a second. And the other one is about how you apply these things on a regular basis using tools like deployment pipelines to make sure that once you define these fitness functions, they get applied on a regular basis. So that's the incremental part of our definition. The last part of our definition is about multiple dimensions. And it's this awareness that you can't really think about evolving software systems without thinking about evolving all the parts of the software system. So this is going to encompass the traditional kind of architectural concerns like performance and auditability and scalability and things like that. But it's also going to concern some things that you don't normally think of as purely architecture like relational database design. We have a chapter in our book about evolutionary database design, but it's really just a symlink to the Refactoring Databases book, which is the really canonical source for that. Security is also one of those things, because what we're trying to do here is make people realize that a bunch of things that you used to consider different categories of things are actually the same category of things. Security is an architectural characteristic you need to support. Can we figure out a way to automate the support for that, et cetera? I'll give you an example of that in just a second. So let's talk a little bit about automating governance, because that's really where we are here with things like fitness functions, is the ability to automate governance. Deployment pipelines make a great place to apply these fitness functions as you've created them. So let me give you a few examples of some fitness functions that we've created for some clients. One of our clients got really worried, their lawyers got really worried about the legality of open source libraries. And so the developers went and found all the open source licenses for all the libraries, let all the lawyers look at them, and then one of the lawyers asked a really awkward question. What happens if one of these open source libraries changes their license terms? And we assured this lawyer, trust me, every open source project on earth has a staff lawyer that manages legal changes and is very careful to notify every project on earth that's using that. No, of course not. It's some dude in a basement somewhere. He's never even read that license file. He copied and pasted it somewhere else and dumped it in his framework and then let it go. So there's no governance in the world of those licenses, but this lawyer is really concerned about this, because what if you introduce a viral license? So we built a fitness function. What our fitness function does is hash the library and put that value in a database. And now every time that library updates, we rehash the library, and if it changes, we fail the build and call the lawyer. Hey, it's changed, you need to come look at the new one. Is that okay? Okay, we'll hash it, put it in the database, we're good. So we didn't try to build a fitness function that doesn't analyze, how these things fit together. We just failed on change and now let the human handle it. Here's another example. So I was working with a company that had a lot of very inexperienced developers. And so the architects put the fitness functions in place to keep things under control. And so this inexperienced developer was tasked with writing some code that did something with all 50 states in the US. So being an inexperienced developer, he wrote a method that said if state equals Georgia, then do this, else if state equals Alabama, then do this, else if state, for all 50 of them. But the architects had put a fitness function in place that said fail anything with a cyclomatic complexity over 30, because that's just ridiculous. And it failed. And my friend Clint Vandenberg has a great quote, that bad developers will move heaven and earth to do the wrong thing. And so this junior developer thought, it won't let me do that. Oh, I know. I'll just move that code up to JavaScript on the front end. Problem solved. So went up to JavaScript on the front end, wrote the same 50-line method for all 50 states, but the architects outsmarted him because they had a fitness function on the JavaScript code too. He tried to check it in, it failed. He's like, damn. What am I going to do now? And so he finally had to go to the architect and say, hey, look, it won't let me check this in. And that's the day he learned about the strategy design pattern. This is governance to try to keep things in control on projects and keep them from spiraling out of control. This is a way to control things that happen on projects like that. So one last example about this. Well, actually, I'll get to that in just a second. So one of the lessons from the DevOps world is once you've created enough automation, you've created a platform. So let's assume for a moment that all of your projects were running a deployment pipeline. And most fitness functions are going to be really local to projects. But let's say that your security team has a stage in deployment pipeline. And maybe it does simple penetration testing, or maybe it's making sure that you don't check passwords into version control and other simple things like that. What happens in your company right now if a zero-day security exploit comes out with one of the frameworks that you're using to build software? This is not an abstract question. This happened to a major financial institution in the US recently. And what did they do? They found out ZeroDay Exploit, one of our core frameworks. They ran around, tried to find all the projects and fixed them. What's the lesson about manual ad hoc work? What always happens? Things fall through the cracks. And this is exactly what happened to them. Half a dozen projects they didn't realize were running this affected version, and they got nabbed big time. What if every project was running a deployment pipeline, and the day that exploit came out, your security team inserted a test that said if this project is using this affected version of struts, fail their build? Now, no affected code will go live because they can't be deployed, and now you know every single project that's affected, and now we can go fix those things. Automating governance allows you to keep things from falling through the cracks, including things like architectural governance. So once you've created these things, how can you publish it? So one of the things that we talk about a lot, in fact, we're doing an exercise out front here, is this Build Your Own Technology Radar exercise. We release this as a white paper a couple of times a year, but we're seeing more and more of our clients actually use this as a kind of a governance tool because it makes a really good metaphor for the things that we're really trying to support within the enterprise. Those are things to adopt. The things that we're trying to deprecate and move away from are in hold. And so this is a great way for enterprise architects to get together and crowdsource the things that we're really trying to support as an enterprise versus not. This is that great illustration of guidance from the enterprise architects, because we're not forcing you to use any of these things, but anything adopt means that this is perfectly now suited for our enterprise. We know it works well. Things are in trial. We're doing research and development on, so if people are wondering why are we not using Vue.js yet, you can go there and say, oh, 3 projects are experimenting with it, and things are on hold means that these are things that we're actively moving away from. We built some tooling and open source this to help you build that same visualization for yourself if you want. You put all the values in a spreadsheet, and then you can put it through this tool and build the exact same visualization we use for our stuff. And we've open sourced that so you can host it yourself. And so this is a way that you can actually publish that governance within your organization and maybe support that kind of guidance kind of supporting constant change. So last thing I'll talk about is a great example of the kind of operational side of incremental change. And this is a story from the GitHub engineering blog called Move Fast and Fix Things. And this tells a story from GitHub about merge. So it turns out since day one at GitHub, the way they have merged 2 Git projects is to shell out to a shell script, have it do command line Git merge them, and then suck it back into GitHub. And that works flawlessly because command line Git knows how to merge things. The problem is it doesn't scale particularly well. These are really aggressive, agile organization. They average 60 deploys a day. And this engineer said they operate at such scale that every edge case appears almost instantly. And so now they need to bite the bullet and replace merge. And so they wrote the new in-memory merge code, and they did their due diligence testing on it. But here comes the scary part. Now we need to put it live. But here's the problem. You can't break merge. Merge has worked flawlessly since day one. The last thing you want to do is introduce regressions into this thing that's been stable as a rock forever. But this is a really common problem in architecture. How do you make substantive structural changes without introducing all these rippling side effects all over the place and making the whole thing unstable? The way these guys did it and open sourced it so you can take advantage of it is create this tool called Scientist. And not only did they create this, they open sourced it to a variety of other platforms. So if you go to the Scientist link, you'll see where they've ported it to other languages. Here's what Scientist allows you to do. It allows you to conduct experiments. And so for every Scientist block, it has a use and a try. The use is the old thing we used to do, and the try is the new thing we're trying out. So when you fall into an experiment, Scientist decides whether or not to run the try block. For the merge experiment, it did it for 1% of the cases. It always runs the use block, and that's what it always returns to the user. So the worst case scenario, if you're the user here, is you get exactly the same answer you would have gotten back before. But it's also running the try block in the background. It randomizes the order in which these things run. It measures durations, compares results, swallows and records any exceptions, and publishes all this stuff live. When they went live with this experiment, this is the number of merges they were doing. You can see some tiny ticks along the bottom, which are places where they disagreed. So here is the blown up view of the bottom. So here's a place where try and merge disagreed. That's a bug in their code that they now need to go chase down. And so they did. But they're also testing performance. So here's the performance, and the performance is much better. The green line is the new code, and the blue is the old code. They ran this experiment for 4 days. Until they got 24 hours with no mismatches or slow cases, removed the old merge code and left the new merge code in place. Over the course of that 4 days, they ran more than 10 million comparisons between the old code and the new code. So when it came time to leave that new code in place, they had high confidence it was doing exactly what it was supposed to do. This is a great example. A lot of people believe that aggressive agility increases risk. It does the opposite. It greatly decreases risk because it allows you to have the engineering practices to do things like experiments and do exactly things like this. So to summarize this, to support constant change, we need to remove needless variability from our projects because we're not benefiting from that at all. This realization that once you reach a certain level of automation, you've actually created a platform that you can build other stuff on top of. DevOps taught us that lesson, and now evolutionary architecture is teaching us that lesson from the governance space. But it also shows you need to constantly evolve your thinking about how we reuse code, about how we attack problems, because as our ecosystem changes, it literally gives us brand new capabilities all the time, and we need to be able to pay attention to those things to be able to most effectively support constant change. Thank you very much for coming. I hope you enjoyed it. Thanks very much.